This video is part of a series showing the flexibility of a language interpreted on-chain. I present you the EVM1 interpreter subsystem, part of the Taylor interpreter smart contract. It allows you to execute any EVM1 smart contract or bytecode script on-chain without deploying the contract. You don't need to trust off-chain frameworks to test your code. Once an on-chain interpreter is deemed secure, it cannot be changed. You can try multiple variations of the same contract before deciding to deploy one of them, or you can execute contract bytecode and call data directly from storage without deploying. We are in the Taylor editor, and this is the root Taylor interpreter smart contract address, and we can see that it was recently deployed on Ganache. We will start with a basic Solidity smart contract that most Solidity developers know, the ballot contract. And we will compile it right here in Luxor. And we will display the result with table row first in C2. So this is the compiled bytecode. Now, the ballot contract constructor takes in an array of strings which are the proposal names. So we are going to construct that input here. So we will use the ETH ABI encode function, which takes a list of types. In our case, it's a string array, and a list of arguments. In our case, it's a list of proposal names. And we will display the result in another cell in C4. So these are the encoded arguments. The deployment bytecode is the concatenation between the compiled bytecode from C3 and the encoded arguments from C4. So it is just a matter of joining them. And again, we will show the result in C5. And this is the result. If we use the interpreter on the deployment bytecode, we will get the runtime bytecode. So this time we begin with a $, which says run the following function on-chain. And we are going to use the interpret function on the deployment bytecode at C5 and an empty call data value. And we get a result that we will display with table row first at C6. And this is the runtime bytecode. So the interpret function ran on-chain, and these functions with an equal in the beginning were ran on the JavaScript backend. But we don't just want the runtime bytecode. We want to further use this runtime bytecode to execute contract functions. And if we look at the ballot contract in the constructor, we see that it uses storage to save the proposal data. So what we are going to do is run the interpret function as a transaction. So we are going to add an exclamation mark. Okay, and now we will return to have the runtime bytecode here. These are 3 of the ballot contract functions in a human readable format. The ethsig function transforms this human readable format into a 4-byte signature, and we can use this value as call data for the runtime bytecode. C6 we have the runtime bytecode, and in B8 we have the call data. Let's display this result in the cell below. Okay, and now let's decode the result. We can decode it with eth ABI decode, and we need a list of types. And the data from C9. We get the proposal name, proposal 0. Let's also see what is stored under proposal index 1. So we will use this function, which returns a proposal's data given an index. So we start by computing the signature for the proposals function, and we will join the signature with the encoded index for the proposal. And the index is 1. So we have our call data here, and now we can run the interpret function on the runtime bytecode at C6 and the call data at B15. And this is it. Let's display the result properly. And now let's decode it. And we get the proposal data, which is the proposal name and how many votes it has. Before we vote for a proposal, let's deploy an instance of the ballot contract using the deployment bytecode computed here, and display the transaction receipt row first so we have access to the contract address. We will display it starting with E3, and now the deploy function, which will be a transaction, and we are deploying the bytecode from C5. Okay, the contract address is at G4. So now we can use the function signatures from earlier with ethcall, which takes in the contract address and a human readable signature and arguments and returns the already decoded value. And a list of empty arguments. and we get the result proposal 0, which is the same as this one. And let's display the result at F10. And it's proposal 0, the same as the interpreted contract. And we are going to do the same with the proposal data for index 1. And we are displaying the result at F17. The contract address is the same and the signature is at A15. And now we have an argument, which is the index 1. And we get proposal 1, the name, and 0 votes. So now we are ready to vote. So let's prepare the arguments for the vote transaction as we did earlier. So we have the signature at A12 and we have the argument is index 1. So we are voting for proposal 1. And we are going to run the bytecode interpreter, this time as a transaction, on the runtime bytecode at C6 and the call data at B12. And we will expect it to appear here in Ganache. And it has appeared, and we see that the gas used is 400,000. Now let's run the winner name function again. So it's this one. And now the result is proposal 1. And if we run the proposals function again, now we see that we have a vote. Let's run the vote function on the compiled contract and display the transaction receipt starting with F12. So this will be a transaction, and it will take the contract address and the function signature at A12. And the index for the proposal, which is 1. We have the transaction. Gas used 83,000. And we can see the transaction in Ganache. Let's do the same here and run the results again for the winner name, and now it's proposal 1, the same as the interpreted side, and now let's see how many votes proposal 1 has, and it's 1. To summarize, we have executed ballot contract functions in parallel by interpreting the bytecode on-chain and by running the compiled bytecode classically, and we got the same results. The gas cost, of course, increases when the transaction is interpreted, but the flexibility advantages of an interpreted language are very interesting. And in the case of Taylor, you can have a new simple upgradability mechanism. You deploy an interpreter contract once and then add, update, remove functions to and from storage. This system encourages pure functionality, creating reusable pure functions, and the solutions become portable. Functions work across multiple deployed interpreter contracts, and you can take a function developed by someone else and integrate it in your script. With common functionality comes tighter integration between ecosystems and programmers. So the Taylor system maintains synergies between the on-chain storage and caching system, Luxor or spreadsheet, which is a flexible client for function consumption, dtype, an extensible type system and type database, and the Taylor functional language.